In this section of Chapter 9, I will talk about hybridization and bond angles, and then resonance. Now let me give you a simple background why we need hybridization and how we determine hybridization in a molecule. Now that helps in determining molecular geometry. Now basically hybridization means mixing orbitals to obtain identical orbitals. Let me give you a simple analogy. Flour and water gives you dough. And then why do we need dough? To bake bread. Now the question is dough flour or water? It's neither, it's mixture of both. It's combination of both. Similarly, if I have orbitals coming from two different atoms, when I mix them together mathematically, we get hybrid orbitals. So hybrid orbitals would have their own properties, but you'd have the same property throughout. So you'd see them when we give you specific examples of hybrid orbitals. Why do we need hybrid orbitals? To make a molecule. Now here we're showing you actual mixing. Of course, these are all mathematically done. Remember, I mentioned before that each orbital is represented by a wave function or a wave. So anyway, these are mathematically, these are done. When you mix S and P, you're mixing two orbitals and you end up with two orbitals. And this is one of them. This is the second one. And at the center you have the atom. So central atom and two hybrid orbitals. They're directed opposite from each other at 180 degrees away from each other. Now here you're looking at hybridization of S and 2p orbitals. So that's called sp2 hybridization. Here we are mixing three orbitals and we'd end up with three orbitals. And this, again, this is the central atom shown in red, and this is one of the sp hybrid orbital, sp2 hybrid orbital. This is the second one. This is the third one. So when you mix three orbitals, you end up with three orbitals. Now, in this case, these hybrid orbitals would be directed at an angle of 120 degrees from each other. In this slide, you are looking at hybridization involving 1s and px, py, and pz orbitals. Since we are mixing four orbitals, we will have to end up with four orbitals. And those four orbitals are shown at the bottom. So these are the four orbitals. And again, I'm going to show you the central atom with the red dot. So, and the angle between these hybrid orbitals is 109.5 degrees. So keep in mind, sp hybrid orbitals are at 180 degrees from each other, sp2 at 120 degrees from each other, and sp3 109.5 degrees away from each other. Now the question is, how do I know when to have sp hybrid orbital, when to sp2, sp3? So let me show you a simple way to determine that. So let me first write down different orbitals. I'm going to write down S, Px, Py, Pz. Then you have d orbitals, dz square, dx square minus y square, then dxy, dyz, and dzx. So that gives all five d orbitals followed by three p orbitals. Now, say central atom has two pairs of electrons. For each pair you need one hybrid orbital. So for two pairs, this is how you're going to combine. Since I have two pairs, I'm going to combine these two. So that would give me sp hybrid orbital. And you can see here, indeed, sp hybrid orbital. By saying sp, we talk about combining s and px orbital, and that gives you two hybrid orbitals at 180 degrees from each other. Now in case we have three pairs of electrons on the central atom, remember I said that for each pair you need one hybrid orbital. So what kind of mixing I need? I need to mix three orbitals, and these three orbitals, the first three, you're going to combine, and notation would be sp2. So let me write down these now. sp goes with 180 degree, sp2 goes with 120 degree. Now if we have four pairs of electrons, again I'm going to combine first four. Okay, let me use a different color. So now I'm going to use S, Px, Py, and Pz. So that would be sp3 hybridization, and that goes with 109.5 degree angle. So 109.5 degree angle. What would happen if I have more than four pairs of electrons? I may have five pairs of electrons. Then I'll have to combine five orbitals. Again, starting from S, you'll have to go to the right. So 1, 2, 3, 4, 5. So I'm going to combine these five orbitals. So you can write down as sp3d hybrid orbitals, but conventionally we write down d first. So we can write down dsp3. You can count that 3, 4, 5. So I combine five of them. Now what would happen if I have six pairs of electrons? Then I need to combine six orbitals. That way I generate six hybrid orbitals, and each hybrid orbital would have then one pair of electron. So now I'm going to show you. For six pairs you're going to go up to that, starting with s, px, py, pz, dz squared, and dx squared minus y squared. That gives you altogether six. Let me double check. 1, 2, 3, 4, 5, 6. Yes. So I'm going to write down as d2 sp3. You can also write down as sp3d2, but more conventionally d is written down before s and p. Now here we're showing you again the different molecular geometry and hybridization. Again, we'd be looking at either electron pair or electron domain. For example, in case of carbon dioxide, CO2, there are two electron domains. For each electron domain, you need one hybrid orbital. For two of them, you need two hybrid orbitals, and that would be called sp. Remember, we just mentioned sp goes with 180 degree angle. So let's write down. In the future, this would be very useful. Similarly, in next molecule, I have three pairs of electrons. So I need three hybrid orbitals. So sp2 combination would give me three hybrid orbitals, and angle would be 120 degree. For four pairs of electrons or four electron domain, I'm going to get sp3 hybridization, and that goes with 109.5 degree. Sometimes this angle could be a little bit squeezed, especially when you have unshared electron pair or non-bonding electron pair, like in this molecule, NH3, which we discussed before. So that unshared electron pair or non-bonding electron pair is going to squeeze the other bonds so that they become smaller than 109.5 degree. You see the even greater effect on H2O, having two pairs of electrons, non-bonding electrons, on oxygen, and that's going to squeeze two H atoms, OH bonds, even to smaller angles. So in case of water, the HOH angle is around 104 degree. So about it's decreased by about 5 degree from tetrahedral 109.5 degree. Now here we have 5 electron domains or 5 electron pairs. As I mentioned before, I need to have 5 hybrid orbitals, and dsp3 gives me 5 orbitals. and that has combination of two angles. So let me draw the triangular planar angle. We talked about this without discussing about hybridization. So there are two sets of angle. Within the triangle you have 120 degree. So let me show you. Within the triangle you have 120 degree, and outside those perpendicular ones are 90 degree. So you have combination of 90 degree and 120 degree angles. D2sp3 gives you octahedral geometry, and all the angles in this case is 90 degree. Now we discussed before that we may have trigonal bipyramidal or octahedral electron pair geometry or electron domain geometry, but molecular geometry could be different depending upon how many of those electron pairs get bonded. If all of them get bonded, then molecular shape would be same as electron pair geometry or electron domain geometry. Now let's look at these two problems from the book. In this case, carbon triple bond would be considered to be one electron domain. So around this carbon, there are two electron domains. So two domains means sp hybridization. So right away you can predict the angle will be 180 degree. Around the other carbon is the same thing, 180 degree. So you have 180 degree around both carbon. Now let's look at 31D. Let's first focus on the carbon shown with number 6. Now around this carbon you have a double bond, that be single electron domain. So let's see how many electron domains we have. 1, 2, 3. Around that carbon we have 3 electron domains, and 3 electron domains would have sp2 hybridization, and that goes with 120 degree angle. Now let's look around the oxygen shown with number 7. We have 1, 2, 3, 4 pairs of electrons, and that gives sp3 hybridization. So let me show you which 4 pairs I'm counting. This is the 4 pair. sp3 hybridization because of 4 pairs. Same would be the case with 4 domains. So this is going to give 109.5 degrees, slightly smaller. So I'll just put down smaller because of two unshared electron pairs on oxygen, which is going to squeeze the bond angle. Now the last one, let me show you with a different color. That carbon has 4 pairs of electrons. All 4 pairs are bonded, and here you'd have sp3 hybridization, because for each electron pair I need one hybrid orbital. For sp3 would give me 4 hybrid orbitals, and it goes with 109.5 degree. Okay, again, let me write down some of these sequence I already wrote down before in case this helps you. Px, Py, Pz. Now, if I need 4 hybrid orbitals, I'm going to combine these 4 orbitals, and that will be called sp3. If I need to have 3 hybrid orbitals, I'm going to combine these 3. So that gives you sp2. And sp2 goes with 120 degree. sp3 goes with 109.5 degree. In some cases, of course, it could be squeezed to a smaller angle depending upon how many unshared electron pairs are there on an atom. Now, valence bond theory describes hybridization that we already mentioned. Now, there are always 2 ways orbitals can overlap, and we're going to show you those 2 different ways of overlapping of orbitals. In this molecule, you're seeing this. one kind of overlap is called head-on overlap. It's like shaking hands. You have a good grip. Like on the left-hand side, the central carbon atom has 3 sp2 hybrid orbitals. The right-hand side carbon also has 3 sp2 hybrid orbitals, and shown with the label. And those 2 sp2 hybrid orbitals, they overlap each other. So it's like they are having a good grip. And that overlap forms what is called sigma bond. So sigma bond is formed by head-on overlap. An electron pair lies along the line joining the two nuclei. So let me identify one of these sigma bonds. This is a sigma bond. Actually, all these overlaps that you're seeing here, that forms a sigma bond. So keep this in mind. In this molecule, we are showing you only the sigma bond at this point. And keep in mind, these are also sigma bonds, even though we didn't identify them. A carbon-hydrogen bond, those are sigma bonds, because there is a head-on overlap. Now this is the second kind of bond. Those two p orbitals, say this is pz orbital, and this is also pz orbital. Even though in the figure they're shown separated from each other, but truly they're pretty close to each other, and they overlap laterally or sideways manner. So that means if you think about that, these two carbon atoms are much closer, then these two sides are going to overlap. But this overlap is not going to give much stronger bond because it's a sideways overlap. It's not head-on to have a good grip. Now this gives rise to what is called pi bond. So this is a pi bond. So sigma bond is formed by head-on overlap, and pi bonds are formed by sideways overlap. So if we ask you this question, which one is stronger, sigma or pi? Obviously your answer would be sigma, because sigma you have a head-on overlap, you have a good grip. Pi has sideways overlap and it doesn't have a good grip. So that's why pi bond would be weaker. In most organic addition reactions, that's why pi bond would break down. Now, multiple bonds we often get confused because Lewis structure doesn't distinguish these double bond or triple bond. So on paper it looks like they are all identical, but truly that's not. In this compound, the one is sigma bond, the other one is pi bond. In case of triple bond, one is sigma bond and there are two pi bonds. So keep that in mind. Now, we are going to discuss resonance or delocalization of electrons. Now first you need to get Lewis structure for NO3 minus. This is NO3 minus. So you add the valence electrons for each of these. For nitrogen, you look at periodic table and count electron from left to the right along the same line along which you have nitrogen. Like nitrogen appears in line 2. So it would be 1, 2, 3, 4, 5. It's the fifth element as you count along that line. So there are 5 valence electrons on nitrogen, and oxygen is next to that. Each oxygen has 6. So, and 3 of them would have 18. And then you need to have nitrogen electron. These are all valence electrons, keep that in mind. 5 would be added, plus 1 electron for minus. So that gives you NO3 minus. So let me show you that. So 3 oxygen, 18, 6 times 18 coming from oxygen, and nitrogen 5, that's 23, and plus 1 because of minus, because NO3 is minus, so that gives you 24 electrons. So this is how you're going to write down, as if nothing was shown on the screen. Let me show you how we can start it. Central atom, the atom which is present in least number. So what we're doing is writing down Lewis structure for NO3 minus before we write down resonance. So N is the central atom, and then write down 3 others, O, 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 and then give noble gas configuration to the outer atoms. That means they must have 8 electrons around. 2, 4, 6. Each line represents a pair of electrons. So that's how we got all 24 assigned. Now look at the central atom. Central atom has now 6 electrons, so we'll have to make it 8. Then you can move one pair of electron from one of the oxygens to in between oxygen and nitrogen. So that's what I'm going to do. And that would give you this structure. So it doesn't really matter. You can make any of these, bring pair of electron from any of the oxygen to in between oxygen and nitrogen. And that would give rise to 3 different structures. Now let me show you how we can go from one structure to another structure. Let's start with what you see on the screen, the leftmost structure. This is one of the resonance structures. Now at the beginning you may be confused when you can write down resonance structure. Resonance means there'll be more than one way of distributing its electrons. In this case, location of the double bond. There must be a good passage for those electrons in order to give resonance structures. So if I'm going to bring this electron pair to in between nitrogen and oxygen, then the nitrogen, central nitrogen, would have too many bonds temporarily. So it will have to break one of its bonds. And if the pi bond is going to break, and it will put on the top of oxygen. So that's how you end up with second structure. So from one structure you get the second one. And actually the charge is now, I mean, if you look at the formal charges, I mean, it would be like each oxygen with single bond would have -1 and nitrogen would have +1. Now, if you forgot about formal charge, let me remind you this, how you calculate formal charge. Now, let me show you around nitrogen. Whenever it's the bonding pair, you just take half of that. So 1 for the single bonded oxygen, 2 for the second single bonded oxygen, 2, and for the double bond, you get 1 for each of those bonds, so that's 4. So nitrogen would get the share of 4 electrons in this bonding pattern, but valence electron of nitrogen, if you look at periodic table, is 5. So out of 5 valence electron, it now has 4. That means it's lost 1 in this kind of sharing of electron. So nitrogen gets +1. In the same way, you can count charges on this oxygen. 2, 4, 6, 7, because you get 1 of the shared electron. So that's 7, and oxygen is supposed to have 6 valence electrons. Now it has 7. So let's write down so that you know +1, this is -1. In the same way, the other oxygen is -1. But this oxygen on the far left with double bond would have no charge because you have 2, 4, 5, 6. It's supposed to have 6 valence electrons and it does have 6. So there is no formal charge on it. When you add up all these formal charges, you can get -1, and it's supposed to be -1. NO3 is -1. So I just want to remind you this, because quite often with resonance, we also assign the positive and negative charges. But overall charge is -1. Now, how do I go from second to the third? Again, try not to repeat any of these. So we'll have to get electron pair from, let me use a different color, from here to here. If you do that, then central nitrogen would have too many electrons, so it has to break its pi bond and move its electron onto oxygen. And that's how you get the third structure. So these 3 are the resonance structures for NO3-, and overall structure will be given by the combined effect of these 3. So that means we can say that nitrogen would have sigma bond that's fixed. and I'll write down the dotted line indicating delocalization. That's the combined effect of these three structures. Now this is a better picture you can see. Now the top one shows the localized electron cloud between nitrogen and oxygen, and the bottom one shows delocalization after considering the resonance. In case of a benzene, C6H6, again you're seeing all these PZ hybrid orbitals, and they overlap with each other, and they give you a structure like this, delocalized pi. And these are the localized pi bonds before considering resonance hybrid. So let me show you the equivalent benzene ring here. So this is the benzene ring, 6-membered benzene ring, and you have a double bond on this side and double bond on this side. Every other one would have a double bond, and that's what you're seeing here. And you'd have another benzene ring which would have just different location of the double bond. Other than that, it would be identical: double bond, single bond, double bond, single bond, double bond. So you can see that double bond locations are different, and their combined effect would give you resonance hybrid, and that's what you're seeing here.